Everybody, this is the last lecture of machine learning. I'm sad too. All right, so given that this is the last lecture, and we actually lost, so I'm one day short in some sense because of the snow day. Actually, we lost one lecture, and unfortunately, it worked out that I'm exactly one lecture short. That's okay. But that leaves me, or leaves us with a choice. So ultimately, this is your class. So I want you guys to decide what we do. So we can do, there's multiple things we can do today. So I know some people have been asking for a review session. So the exam is next week, in exactly 1 week, I believe, yeah. So one thing we could do is we could go over all the material briefly, kind of do a, a 3-minute mini version of the class one more time and just summarize the important points. That's boring but useful. Another option is that we can continue on deep learning and I can talk about convolutional neural networks. I know a lot of you would like to hear about it. That's also how you win the Kaggle competition. And then some people asked what's going on in research right now in machine learning. So what's after this class? So one thing I could talk about is what are different areas of machine learning that we did not cover, and what are research topics. So these are, in some sense, these are 4 choices, I believe. So one is review session, one is we talk more about deep learning, one is we talk about other stuff, other classes in Cornell that are about machine learning, like what is unsupervised learning, what is active learning, what is reinforcement learning, all the things we did not cover. And finally, what is current research? And I could show some research that's going on in my lab. So these are the 4 different choices. And so why don't we have a quick vote? And then I decide to ignore your vote and just do whatever I want. All right. So, OK, first one. So first one is review session. So who is in favor of a review session? OK. Oh, it's going to be hard, actually. It's going to. OK. Wait, one more time. Please raise your hand. Only one hand. Okay, all right. You may have to come down to one more vote, like in France. Okay, that was review session. Second thing was deep learning. Who wants to do more about deep learning? Oh, okay, review session is out. All right. Third one is other classes at Cornell. Nobody. Okay, forget about other classes. What is it? All right. And finally, current research that's going on. Oh, okay. Well, is that a majority? Okay, one more time. Deep learning. Okay, how about current research on deep learning? How about this? All right, okay, good. We have a winner. All right, okay, good. So we can do this. That works fine. So what I need to do, though, is I need to give you a 5-minute explanation of what ConvNets are, actually, because that's what current research is on. So in the last lecture we've done, in the last couple lectures, we've talked about deep neural networks. And if you remember correctly, and I've summarized this now many times, you basically say you have a function that takes as input some data instance, and you would like to make a prediction that's W transpose phi of x, where the trick is that phi actually is another function inside that function that looks something like this. And for those people who've implemented the homework, you know all about it at this point. And I realized every single lecture I call this something else. U. All right. And this again can be phi prime of x. So you basically have this nested, these multiple layers of, in this case we have just one hidden layer. OK, so that's great. And that's what people call a fully connected network. And a fully connected network means if I write this as a network structure, if I take my original input and I write every single dimension as one of these circles, this is my x, then what I learn is first I learn phi of x, I call this phi prime of x, then I learn phi of x, and then I learn my h of x. And every single dimension of this function here has as input every single dimension of the previous representation. So this is where this notion of network comes from, and it's fully connected because everything is connected with everything else. And that's the most general form. And, you know, of course, you can draw this out. And at the end, you basically have one-dimensional or multiple-dimensional outputs. So that's great, and that's very, very general. But turns out when you work on images, you have a lot more information. And you would like to incorporate that information into your classifier. And in fact, if you take your image and you represent it as a vector, right? You have an image that consists of 6 million pixels, right? That's, you know, whatever the resolution of your iPhone camera. And if you vectorize it, then every single dimension corresponds to a pixel. The problem is you've now thrown away something, right? You've thrown away the fact that actually it was a two-dimensional image, right? And, well, you say, you know, it's not a problem, right? Like this, in some sense, I just represent it differently. I just represent it as a vector. But turns out natural images have very specific features or very specific properties that don't apply to data generically. And that is, let's say I have a little picture of, you know, some good-looking person like me. Here we go. And if I now, you know, if you classify this and you say, okay, this is whatever, person X, right? If I would now move this person and move it a little bit to the right, right, it would still be the same person. Right? If I move it a little bit up or down or something, right? It wouldn't change. But this vectorial representation would change drastically. And it would look completely different because the pixels would be completely different of those two images. And we call this translation invariance. So images are locally translation invariant. So if I take any part of the image and move it a little bit, the image actually, the semantic interpretation of the image does not change. And that's crucial, right? And the reason it's crucial is because if I train a neural network to recognize objects in an image, if I want to learn this here is, you know, whatever, person X, this here is, you know, whatever, let's say Donald Trump or something, and arguably less good looking as I am, if you know, it would always recognize if it's exactly in this position. But if you actually have him over here, right, you wouldn't recognize him anymore. So what you would need is you would need training data in where, you know, it's basically in every single part of the image, right? So you have one image like this and one image like this, etc., right? So you need millions and millions of images. So what convolutional neural networks do is they change this function phi to incorporate that. So basically say, if you would change your data input a little bit by just moving things around, it won't change the output. And turns out that's the big hit. Like that made all the difference in the world. Because it reduces the amount of data that you need to learn something exponentially. Losers. What? Next. Well, I agree. Oh, let's keep that. That's good. I like it. All right, good. So what convolutional neural networks do, they take an input image and they respect the fact that it's an image. And so they actually say the image has multiple channels. So actually, typically what you have 3 channels. So what that means is if you have an image that has natural colors, you can divide that into red, green, and blue. Right? So if you have 3 images where this one just shows you, oh, the red, you know, how red every single point is, this shows you how green every point is, and this is how blue every point is. And if you add these 2 up, you get the color image. So you take that as an input to your function phi. So this is my x. My x basically consists of 3 different images. And what my function phi now does, it takes that input, and then it generates new images. And this doesn't have to be 3. It could be many. It could be 100 or something. It doesn't matter. Right? And then my next function, phi prime, takes these as input and generates another, whatever, 100 images and stuff. So you never, ever, you know, destroy the image form. And only at the very, very end do you get a final representation and, you know, output some h of x, which is actually, so maybe here you actually have some fully connected layer or something. Okay, so far so clear? Raise your hand if you're still with me. Okay, awesome. So how does this work? And the trick is the convolution operator. So what this function phi does, it actually has a little, you know, instead of actually taking a weighted average, this image here actually is associated with a particular convolution. Who's heard of convolution? Raise your hand. Okay, so basically what you do is you have a little teeny little image of maybe 3 by 3 pixels. And what you do is you move that image around. So you start here, and you multiply this pixel with that pixel, and this pixel with that pixel, and this pixel with that pixel, and you sum them all up. And that gives you a value, and that's the value here. Okay? And now what you do is you take this and shift it one to the right. So now you take this pixel here and multiply it with this pixel, and so on. You sum them all up, and you get this value here. So you take this little image and just move it around and compute the inner product everywhere. And that gives you an image here. So what that does is essentially you're kind of blurring the pixels, right? So the pixel here is an average of the corresponding pixels around the same location in this image. So that's what you're doing. But it's a weighted average, and that's the key. So these weights, these values here are actually weights. They basically tell you how much do I value, how much do I weigh the pixel here, here, and here, for example. Right? And imagine you had strong weights here, but low weights here. What you would be doing is you would get a large value if in the image here you have something similar. You also have, something like this. And so what you're essentially doing is you detect edges that look like this. Right? So what's happening is that these images here, what they are doing is they are basically detecting local features in an image. So some of them detect edges, like straight edges, or horizontal edges, vertical edges, circles, etc. And you keep doing this. So initially you just have very low level things that you're detecting. And so you get these images here that basically highlight certain features, or highlight edges, or highlight circles, or highlight something like this. And then here basically you highlight more complex things that correspond of so for example here you could be highlighting eyes, right? Eyes consist of edges and circles. And so our eyes all look pretty similar, actually. Like no matter what you tell your date, right? It's actually they all look pretty similar. So basically what you can do is you can build an eye classifier somewhere here that basically is a kernel that basically goes over the image and scans for eyes. That's essentially what they are doing, right? And you have these little things that basically check for eyes, right? But these things here again consist of little, is there an edge or is there a circle or something? Does that make sense? So you're building more complex pattern detectors. That's essentially what it is. Yeah?
So after you convolve, do you pass it to a nonlinear operator?
You're right. So you do actually have nonlinear, you have ReLU functions in between. Yeah. So these are actually ReLU functions in here. That's right. So you set everything that's negative to 0. Right. You have to have this. Otherwise you just have one linear operation. Yeah. Good point. Okay, does this make sense? Any questions? And the way you train this is just the same way. Turns out actually the convolutional neural network is just a special case of this, right? So you could actually view that this here is one pixel in this image here, right? And what I'm doing is I'm basically, setting 0 weights to almost all of it and just attaching it to, just to the first 3 by 3 pixels here. So these are the only connections that actually have non-zero weight. Everything else has a 0 weight. So you can take a fully connected network and make it identical to convolutional neural network. So a fully connected network is always more powerful. But the problem is it's too powerful, right? By restricting your network to only learn functions that are translation invariant, you actually make it easier for the network, right? You're saying whatever I'm learning, it has to be something that if I shift the image around a little bit, the content of the image around, it shouldn't change much, right? And that's crucial. That's very, very important to understand natural images. And if I would say the big success in deep learning was essentially in these two domains. So one was speech recognition, and the other one, but by vastly more successful, is images. So convolutional neural networks is really the area, or computer vision is the area where deep learning is much better now than anything else. Right? So it used to be that computer vision used all sorts of different paradigms, SVMs, etc., boosting. Convolutional neural networks have really, in the last 2-3 years actually, taken the computer vision conferences by storm. And nowadays, it's if you go there, you don't see a single paper anymore that doesn't have convolutional neural networks in it. Yeah?
So you were talking about translations. What about rotations?
Yeah, so they're actually also a little bit rotation invariant. Not all that much, right? but a little bit. Because you're blurring, but if you blur, if you rotate a little bit, it still looks the same, roughly. Right? That's a good point. You can explicitly code that in, but it gets more complicated. The nice part about neural networks is that they consist of very, very simple building blocks, but you can learn very complex functions that way. And so here, this convolution is a really simple building block. Yeah?
You know how usually like your h of x at the end is something like for classification? If you wanted to generate stuff, like how you did research where you generated images, do you just make your h of x have so many outputs that it could be like an image and you set your loss function accordingly? Or like how does that work?
I will get to that. Actually, that's exactly what I want to show you, actually. So maybe I can show it to you. So, okay, any more questions about convoluted ConvNets? So actually what I'm going to show you now is research on ConvNets. So basically trying to improve the state of the art. And I will try to go over it slowly. But please feel free to ask me questions. You learn them. So you do backprop. So the question is, how do you learn these convolutional kernels? Where do they come from? And the answer is you learn. That's exactly what you learn. Those are the weights of your neural network. This is a talk I gave very recently at NVIDIA, actually, NVIDIA Corporation. They are very interested in deep learning because they sell GPUs. Why don't I actually quickly go over this? So this is kind of a summary. This is how I summarize to them deep learning. And it starts with the perceptron, right? So the perceptron invented 1957 at Cornell. And the idea, you know this very, very well. You implemented it yourself. You just have this hyperplane that separates positive and negative points, right? And so let me just write a perceptron as a neural network, right? It basically is the following. You have your input, and it's directly connected to the output node. And every single connection is just one weight, right? So if you look at the neural network graph, right, you encode an inner product, W transpose X, just as this graph, right? So the value of the node here is the input. This is my different dimensions here, x1, oh, I don't have a, x1 to xn, or xd. And then you multiply them by the weight that's associated with every single edge. So I don't know if you can see this. You have my x1 multiplied by w1. And if they come together here, then that means you add them up. OK, does that graph now make sense? Raise your hand if that graph makes sense. OK, awesome. Right, so when people talk, this is in some sense the way people did think about neural networks. And actually, I love these graphs, actually. It's not that I think they are bad. The problem I have is when people start relating them to things that's going on in the brain, because often that's less helpful. So, one second. So, in deep learning, the only difference basically what we're doing is we have one additional transformation w, right? We have our x, and we just applied x times w, right? Then we have our nonlinear transition function, which in this case is the rectified linear unit, and then we apply our linear classifier, right? So this here is my phi of x. For the longest time, if you think about what a kernel is, a kernel takes your data and maps it into a very high dimensional space. So for a long time, people just thought, what you need to do is you just need to take your data and map it into a ridiculously high dimensional space. And that's very, very good. And that was, in some sense, we could show that theoretically is just as good as a deep network, right? But it turns out that in practice, actually, if matrix multiplication is cheap because you have GPUs, then it's actually better to have just many of such layers. And that's the new thing that came out in the last couple of years. But suddenly, GPUs are fast enough to actually train these things. So just one more time, here deep network, all we have is like x multiplied by w, then we have a rectified linear unit, then we multiply by another matrix, and so on. Right? And matrix multiplication here is just a fully connected graph. So, yeah, so deep learning really, really works. So here's the interesting thing. So here comes my research. So that's something that my group and I have been developing last year. And basically try to fix a problem. And here's the problem. So these are kind of the way the new neural networks look like. They are very, very deep, right? So if you look at new neural networks, now people have even 50 or 100 layers or something. And so one thing that's kind of going on in your network is what you're doing is you're playing a game of telephone, right? Is it called telephone? Yeah, telephone. Where the first layer is that this guy here is the input, right? And it sees this car, and then you kind of talk to each other until the last layer, right? And the car says, like, it's a car, right? And the reason the game telephone is fun, right, is because people always mess up, right? And then you say something else. So here we have, she says bar, right? And then, so because this person only hears the output of this layer, the final output actually is wrong. Okay? So in some sense, the reason that the game telephone is set up in a way that basically you have every single person is a bottleneck and you're just waiting for someone to mess up, right? Well, that's exactly the setup we have in our neural networks, right? So we have many, 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 many layers. Then what happens is that each one of them, if that messes up and extracts the wrong features, doesn't really fire properly, everybody else afterwards is, looks like this. So the problem is during training you can't tell, because during training actually these layers don't mess up, right? Or if they mess up, we just do a gradient step and they don't mess up again, right? But the question is what happens during testing? And the longer my neural networks are, the more likely it is that eventually I will mess up. So what we're trying to do is we're trying to reduce the impact of layers. And so one thing that someone introduced is a very influential paper, and this was 2016. Kai-Ming He from China. And he had this great idea where he basically said we make additional connection. We connect the output here to this layer. So if this guy messes up, we still have the information here around it. So in telephone, that kind of would be, you listen to the person before you, but you can also listen to the person before that. He said, like, what did you say, right? And that reduces the probability of mess ups. That kind of works, but you still have the same problem. Like it's still, it's still the issue that during training, these layers don't mess up, right? So what the network learns is that actually you can kind of ignore these skip connections. So here's what we came up with. There's a very, very simple trick, but it's very, very effective. So that's why, I thought it's good to present it today. So let's say you train a neural network, and it's really, really deep, right? And there's a really good trick. You should try it. Next time you train a really deep neural network. Here's what you do. You actually introduce a coin, right? So for every single layer, you introduce a coin. And you flip that coin every time you do a gradient update. And if it's heads, you keep it. And if it's tails, you remove it. So you just basically surgically remove certain layers from your neural network randomly. And then you just pretend the network is much, much smaller. When you now do an update, right, you just propagate forward and then you do a gradient update. Right? So you get your original network. And the next step, you do this again. So now you toss again coins and you remove different layers. So every single time I do stochastic gradient descent, every single time I do an update, I remove different layers. So I'm really kind of messing up my network, right? I do the worst possible thing you could do, right? And so the reason you want to do this, also the one thing that it's not actually, the coins are not all the same distributions. So you don't want to remove the very first layer. You never want to remove the data, right? Then you have nothing to go on. That would be ill-advised. So you have a 0% probability of removing the data. You have a 50% chance of removing the last layer, and you kind of interpolate between them. So when you train, basically, you train this kind of network, right? So every single time, you never see the same network again. It's very unlikely. When you finally classify, you actually take the full network. I can tell you now why this is a really good idea. So here's a really good idea. Here's why it's a really good idea. The first one is, the final network is one that you actually use during testing, is where every single layer is there. That's something you never actually trained on. Right? Not once during training did you see that network. It would be extremely unlikely. So what you're actually doing during testing is, you take an average of all these networks that you trained during training. So you kind of have some ensemble. But the other thing is a lot faster, because during training you only just take these very, very short networks. And finally, you actually have more information flow. I didn't go into this, but the gradient, actually propagating the gradient in so many layers, at the end you hardly have anything left typically. Anyway, let me show you the effect of this. So here, this was the current world record on one of the hardest data sets. So this is actually Cypher 10, but it also works on ImageNet. This is the current era. These are images where we have 10 different classes and we try to classify them into, this is a boat, this is a house, etc. If you take this network and the only change we make is we introduce these coin tosses and remove layers during training, this is the error that we get, right? So basically the error drops drastically. This was the world record at the time, right? So in every single one of these data sets, every single data set we tried, the error goes down. And the reason, this is very intuitive, right? So basically what you're doing is, during training, you're trying to lower the gap between training and testing error. Your training error actually goes up, but your testing error goes down. Right? Because during training, you actually simulate the fact something goes wrong. One thing that my students want to do is they say, okay, well, this is cool. Now we can actually train a really, really deep network. So beforehand, the world record was 110 layers. So they went 1,200 layers, which took about as much electricity as all of Ithaca or something. I'm not entirely sure, but it was a lot. So this is what it looks like. This is 1,000 layers. And that gives you a little bit of an edge. And so they published this, and this was actually got a lot of attention. And then I felt really bad. I was like, what have I done? Right? I've told the whole community to train networks that have 1,000 layers, right? This is like, the amount of electricity on CO2 I'm generating is like, it's the opposite of, what I believe in. So something's going wrong. I felt responsible for this. So I told my students, they were all like, this is awesome. And I was like, no, it's not. It's terrible. You've done something wrong. We went, I don't want to go in that direction. So we came up with something else. And so here's the idea. That actually, in some sense, what a network does is reads the previous state. Every single layer reads the previous state and writes the next state. So you can kind of see a neural network as kind of a function, right? Where you basically read the state, do some manipulations, and write it again. And what we could show is that if we actually just remove something in the middle, that doesn't make much of a difference. Now, that's really weird, right? That basically means that these individual functions, these are my functions phi here, right? They're not doing much, right? They can't be doing much because I just remove them randomly, right? It's like it's always like this. Like, if someone, if you just randomly remove something and there's no difference, well, that didn't do much, right? So we have a ridiculous amount of redundancy. That's basically what's happening in these networks. So here's an interesting thing. Well, let me just explain this. So the problem is, in some sense, we're still playing the game of telephone. Just occasionally we remove people, right? So everyone has to speak louder, right? If you don't know if the next person is still going to be there, you have to speak louder, right? That's basically what it is. So that works, that's better, right? But it's somewhat still stupid. We're still playing telephone. So there's a reason we don't play telephone when we have business meetings. So why don't we do this? Why don't we do that setting instead? Everybody can talk to everybody. So believe it or not, this is something that no one had thought of until this year. Actually, we just showing this. This just got published. We're presenting this next month. So we basically we have an input image, and what we do is we take the first function, but that actually is the input to every subsequent function. So every function basically takes as input all previous functions, right? So this function phi of x, and this function basically takes this function as input, but also actually this layer as input, and all previous layers as input. Let me not go into the details. The beautiful thing about this is that actually you have no more redundancy. Like all of these layers basically, in some sense, learn everything they learn. You can reuse later on. If you do this, just a very small network immediately improves your result. And this is actually currently the state of the art in deep learning. So if you want to do deep learning, you want to win a prize on Kaggle, use dense nets. Not many people know about it yet. We're presenting it next month. So you have an edge for 1 month. And so then, of course, my students say, like, oh, let's make a really, really big dense net. So then actually you can get, there's a 26 million weights. So it's ridiculous, actually. It's illegal in some states, I'm sure. But actually, if you do this, you can pretty much win beat the world record on any data set. All right, good. That's one thing. So just keep that in mind because it works really, really well. So let me ask you. Let me show you another project. So this is something that I asked my students, and so we've worked a lot on these deep nets with images. And so one question I asked my students: so why is it, right, that convolutional works so well on images, right? Like you have this translation invariance, but it's still like it's so amazing, right? Like if you put in this translation invariance into other algorithms, it doesn't help all that much. It's not as good as ConvNets. So why is this? And so I had a conjecture. And my conjecture was the following, that what deep nets are doing, and this is very interesting, by the way. This is transition in machine learning. So machine learning used to be completely deductive. So that means we have some axioms that we think of. Something like boosting, for example, is completely deductive, right? So we think we have weak learners, and we have the following properties. And now we basically, if you assume these axioms, we can now derive an algorithm that is following guarantees. Inductive research is the other way around. When you have something and you try to, like in biology, right? You have the cell, it's made by some, I don't know who made the cell, right? It's alien technology to us. And we try to figure out, we try to do experiments. So in some sense, what we're doing is actually something inductive here, which is very rare in machine learning. So we kind of look at these neural networks and you say, well, what are they doing? What are they learning? And this is basically these very deep neural networks. And so my conjecture was, images lie on manifolds, right? So we know this because otherwise we couldn't do anything with images. And also if you would just randomly sample an image, you would always get noise, right? You could just randomly assign pixels to an image, look at it, it will never be anything interesting, right? So we know they lie in some very small part of the space of all possible images, and we know they're locally smooth because if you take two very, very similar images and average them, you still get something that resembles an image a lot. So what I was claiming is, what deep nets are doing is, with all this convolution, you're linearizing the manifold. And this is not something that's, I didn't come up with this conjecture. I was, this is something that a lot of people people were kind of talking about this. It was in the air, right? Like, how do you prove this though? So here's an experiment. So basically what I'm claiming is like we have this image of this manifold of images. So manifold is basically this curled surface in a high dimensional space. And I claim that this neural network somewhere internally turns this into a subspace. And then actually everything becomes easy. And so this doesn't come from nowhere because at the end the last layer is still a linear classifier. So in some sense what we must be doing is we must be somehow linearizing this. And one thing people realize is if you train a neural network on some task and then you actually just take that representation and you stick in some images for some other task, it still actually works pretty well. So somehow they're doing something more than just learning that task. They're somehow, and the conjecture was maybe they're just linearizing the whole manifold of the images. So here's the idea I came up with. So let's take a problem that's really easy for deep nets, but it's pretty complicated. It's like, do men have beards or not, right? So here we have people, these are all men, and they have no beard, and these have beards. And so I claim that on this manifold, they look really far away from each other. If like take two bearded men and take an average, right? It's not going to look like anything pretty, right? Just because they have beards does not mean they look alike, right? So they're looking all over the manifold. The same with men without beards. You can't just take, two, like, but do people understand this, my averaging analogy? If you have like a manifold like this, if I take an image here and an image here, and I take completely average, it's here. So it's off the manifold. That means it's no longer a true image. Right? Does that make sense? So only things on the surface are true images. Okay? So that's what we realize. If you take two images that are really far apart, right? Take Donald Trump, Hillary Clinton, take the average between the two, it's not a natural image anymore. Right? But that's even true within, just generic people with beard and without beard. But actually a linear classifier works really, really well in that space. So you can train a deep net very easily to classify, this person have a beard or not. So here's what I want to do. I said, okay, well, if my conjecture is true, then I could take a network that's not trained on beard at all. It's trained on classifying dogs and cars and trucks and anything. Now I stick in an image that it's never seen before, this person, and I move him. He doesn't have a beard, arguably. And I try to move him towards the bearded people. then you should get a beard. That was my conjecture. So we tested this. So this is the setup. So what we did is we took this neural network that was actually trained by, not by us, right? You just say, what do neural networks do that other people train? So we took it, it was trained by the University of Oxford, and they put their neural network online, so we just downloaded it. Now we take this image that was clearly they didn't have, right? I know this for sure. So I take that image in, and I represent this image now as all the activations. So what I'm doing is like all the internal, basically, values of the neural network. Make one long vector, right? That's how I represent that image. Okay? Now I take the space, and I claim this is now here in this space, basically things are linear. It's no longer a manifold, it's now a subspace. So here's how I do this. I take additional images of people, man, they kind of look similar to me, more or less. Not George Clooney, he's not there. And without beard and with beard. And I average them. Okay, so this is in some sense the average man without a beard. This is the average man with a beard. And now the question is, if this describes a vector, right? This is the difference vector. So this is the direction of beardedness, right? In this high-dimensional space. If you go along this direction, you should get a beard. That's my hope. If it's a subspace. If it's not a subspace, we're going to move off into La La Land, and it's going to look ugly, right? So now we can take this vector and add it to my image. And now, hopefully this here will now be the version of me with a beard. So how do we find this out? Well, it's quite simple, actually. So we now take this, go back to our neural network. And here's what we do. We just take, this is basically a whole bunch of numbers that basically correspond to values in this neural network. So now we can just populate the neural network with these values. And now do gradient descent, not to change the weights, but to change the input image. And say which input image would give me rise to these values. So which input image would give me this point? Okay, so I'm just reversing things. All right, does that make sense? Raise your hand if that makes sense. Okay, awesome. All right, so do you want to do it? You ready? All right, 1, 2, 3. Here we go. All right, it works. And there's nothing special about me, so you can take other people. These are randomly chosen people in some celebrity data set, so I know some of them. Not personally, I just recognize them. And so we can just take them and add beards to them. But actually, there's nothing special about beards either. So we can just take these images and make them look older, make their mouth open, right? So here we can make their eyes open. This looks a little weird here, but this guy pops out right away. You can make them smile, right? Give them glasses, right? All that stuff, right? And the important thing, though, is that all of these are just linear interpolations. So all I'm doing is I take this image, put it in a space. I'm not training any neural networks, right? I'm just putting it in the space. I add a vector to it and reconstruct it, right? And I'm basically, it's really about I'm proving a point, right? The point is that now I'm in a subspace. In a subspace, everything becomes easy. You can also do something funny. We can take people's faces and cut out the middle part. So this way we move off the manifold, and then we can go back onto the manifold, and then the face comes back. Right? So these are, by the way, these are not the right faces. These are totally different faces. It's just a face. but it tends to give women female faces and men. And this just means it doesn't learn anything, right? It just basically means it has learned a space in which basically if I go back to the subspace, it semantically makes sense, right? So that basically women are in some region and men are in the other region. We can even try this in very high resolution. So this is now 1,000 by, I think, 900 pixels. So this fellow here is, we can now take this guy in, and move him along the direction of beardedness. And so this is what we get. We can go back again, right? And so it's not bad. You can look at your boyfriend and say, like, well, maybe stop here, right? Like, this does my, So of course, I can't even believe, like, when I went to my lab, like, every time, like, my students are hiding something. It's like, oh, we just made you into a woman, or we just made you. A lot of it, I don't want to see it. Nobody wants to see it. But this is a good one. This basically, I think at the very first lecture I showed this image. This kind of, they took me and aged me, right? I like this a lot because kind of, and they also made me younger, and then went to my wife and asked, is that what he used to look like when you met him? And she was like, yeah, that's kind of what he looked like. Right, so, but you can see basically, you know, this is kind of the progression of age in this. Like, it puts in wrinkles, right, and it puts in, I don't know. Well, that's what I have to look forward to. And anyway. Oh yeah, this is also a good one. So this is a boy. So obviously this is an image that doesn't exist, right? And so, you know. Surprising how much fun you can have, like adding beards on the people. It turns out actually, so it works really well actually for men. Like we've actually had some failure cases where does it not work. And this is also very interesting where it breaks. Because it tells us something. So this is this person here. We gave him a beard, but we also actually changed his race, right? So he looks a lot darker. And what we found is that basically what we did is like the images of people with beard, we try to find similar people. So they're kind of the people that are bald and actually have a beard. And turns out that's actually more common, I guess, in the African American community. So somehow we actually had a vector that kind of pointed in two directions, beardedness and you know, a different race, basically. So we thought that's interesting. In some sense, basically, you could actually do two things. You could basically do two changes, right? First add beard and then change race. And actually, it turns out women is much, much harder than men. Which is for two reasons. A, because the manifold is more complicated of women. And that's because there's a lot more variations going on. So men don't, you know, it's kind of funny. Men kind of all look pretty similar, actually. So there's, women have more variety in terms of lipstick or, you know, like makeup, and the hair is much more variety compared to men. So what you would need a lot more data, but actually we got our data from the internet. Actually turns out there's, we get celebrities, actually a lot of them as politicians. So there's a huge bias towards men. So we actually had fewer women, but we would have needed more women. So this is something that I think it shows you basically how densely sampled the manifold is crucial. I think that's the last slide I have on that project. Is there any questions to anything that I talked about? Okay, good. Then I can actually, you know what? I can actually show you one more demo. Okay. Yeah.
Sorry, can you talk more about the connection between the densely connected net and drop off? Like when you train it, do you still do drop off, or for example, can you implement drop off by
drop out? Drop out, you mean? Oh, see, our dropping layers and dense nets?
Like when you train CNN, there's drop off, randomly turning off units and things like that.
Sorry, say that one more time?
Drop off.
Drop out, you mean?
Oh, drop off, yeah.
I see. So drop out, what drop out does, but we are dropping layers, so you shrink the length of the network. Drop out changes the width of the network. Right, so changing the width of the network is not such a big surgery in some sense, right? Because you're just removing a few nodes. If you change the layers, you could actually change multiple layers that you're really kind of breaking the network. So the effect is very different, actually. Dropout used to be, just for those who don't know, it was something introduced as a regularization method. You just take different dimensions and set them to 0 inside a neural network. But it actually has recently, it was very popular for a couple of years and has recently gone away because people now use batch normalization as a new thing. So the one thing about deep neural networks is the area is moving very, very quickly. Every few months, there's completely new papers that come out. And so something that's within the 3 years is kind of the lifespan of any technology. And then new things, new better things come out. All right, good. So, well, I don't know. Who wants to see one last demo? Raise your hand if you want to see one last demo. Okay, sure. Okay, good. So this is less about research. This is, I guess, so what I thought, I was ready for any outcome of this of this vote. So what I want to tell you about the other class. So the other class is machine learning for data science. So this is machine learning for intelligent systems, and the other one is for data science. And the distinction actually is that intelligent systems in this class, what we did is predictions. So we tried to basically say, let's make a prediction, let's try to predict something, like in a self-driving car, or try to predict the stock market, etc., for decision making. In the other class, in machine learning for data science, what you do is you learn that you learn to discover structure in data. So you have basically, imagine you have a data set, you're a biologist, and you try to make sense of it. Then basically what you would like to find cluster structure, you try to find low-dimensional subspaces, etc. So this is something I worked on. And so you saw just now I talked about manifolds. So one thing I've been working on a lot in my life is actually learning manifolds. And so this is in some sense why I'm working. The work I just presented to you, like how we're learning manifolds, this is really something I've been working on for 15 years actually. Like my PhD thesis was on how to learn manifolds. So I've been thinking way too much of my life actually about this. Like the question is, given that data lies in a manifold, how can I learn this low-dimensional representation? And this was maybe 12 years ago. This was a very, very big topic, and I can show you some. Here we go. Some of this is actually an algorithm that was my PhD thesis. Is here you have data that's in a three-dimensional manifold. Sorry, two-dimensional manifold that's embedded in a three-dimensional space. So this is an unsupervised, this is kind of data analysis. This is the kind of stuff you would learn in the other class. And the idea is basically, here's what the algorithm would do, and people thought it was very exciting. I thought it was extremely exciting at the time. You have this data set, it's true, it's three-dimensional, but it's truly two-dimensional. How can you discover this? And what you do is you build a graph and you kind of flatten that graph. So this is what happens. And actually it learns that actually this lies in a two-dimensional subspace. And it's very similar to what convnets are doing. So you actually now can take any point here and move to any other point, and you just move in a straight line. And what you're doing along the straight line actually is it's actually a meaningful distance. Whereas in the original representation, if you would be here in the blue point and you move in a straight line, you would always move off the manifold, right? And you move somewhere where there's no data. So once you have this representation, you can do a lot more with the data set. So does the sound work? I don't know if the sound works. Can I test the sound somehow? I think it's on. Okay, so this was my PhD thesis. I worked a lot on this. And then at the end of my PhD thesis, I had a workshop that I organized. So this was me. And this is not computer generated. This is actually me younger. And this was basically on applications of dimensionality reduction. So if you can basically learn these manifolds, right? If you can do something like this, where data is really truly on a manifold, right? And you can unfold it, what are the applications? And we thought there's going to be so many applications, right? It's huge. So we had this workshop, and people came, and these are the applications that we found. Like every single one was the same stupid Swiss roll data set that was completely artificial. And this is why I got out of that, actually. Because there was absolutely no future to it. So basically what turns out that actually at the time you could really only unfold very synthetic data sets. So now we can actually do it. 15 years later, we can actually learn the manifolds. But at the time, you could really only unfold these very, very low dimension, these kind of synthetic data sets. So I was extremely disappointed. And I gave this talk in front of the entire field. And I was like, basically all our data sets are synthetic. And can't we find a single real-world data set? And so I was like, well, I found one data set that we like, and that's the Swiss roll, the actual cinnamon roll. And so I tried to apply these algorithms on the cinnamon roll. And so this is my own PhD thesis algorithm applied to the cinnamon roll. Let's see if the sound works. I hope the sound works. Roll it, roll it, roll it, roll it, roll it. And this was kind of a competitor. This local linear embedding. Local linear embedding was a different paradigm. You take a manifold, you cut it up into little pieces, they're all linear, and then you stitch it together in low-dimensional space. You can do that too. It's amazing I got a job after this. But yeah. Of course, one thing you can always do is you can just, instead of doing these nonlinear unfolding methods, you can just use a linear method, right? So the most famous one is PCA. So principal component analysis, basically project the data in a low-dimensional space. We can try this too. And the nice thing about linear methods is you can reconstruct the data. So this is the reconstruction. Anyway, ultimately, of course, the whole point is to do something with this data, this low-dimensional data. But it turns out it didn't matter. My co-authors just ate them all. Anyway, that's I just thought it was a funny movie. All right. All right. Thank you all. This was a wonderful class, and I see you all on Wednesday. And my TAs told me to make the exam easier, and I will try.